Okay, so as I mentioned before, chapter 4, we'll talk about dielectrics. What are dielectrics? These are things that are not conductors. And maybe not as severe as insulators, but every insulator has somewhat of a dielectric property. So they are actually built up of dipoles. Again, these molecules can have higher moments, but dipole is good enough of an approximation because you're looking at the molecule a little further away. And this is what is called a classical treatment. You're not too worried about quantum mechanical processes. Well, it's not just that. Even in quantum mechanical processes, you would study, you would still model a dipole, but then you study its properties using dipole moment. You don't need higher moments for potential, okay? So there are a few things about dipoles that you would need, okay? So suppose I have a dipole. So remember, P, the vector P for a single dipole is just Q times D. And we think of this as D over 2 that way, and the other charge is located at minus D over 2. Both are vectors, and you have a charge Q here and a charge minus Q here. And the general expression for P, you know, the integral expression is rho of r prime d tau prime. And we have worked out this expression as well. Okay. So let's calculate the net force on a dipole, the simplest case, when E is uniform. What do I mean by uniform? Some constant vector, right? That means E is equal to some constant vector. Well, it's simple enough. Net force is going to be Q times E0 minus Q times E0, which is why? One charge is positive, the other charge is negative. So the net force is 0. Again, with a slight abuse of notation. It's a zero vector. I mean, it's a force that is 0. So if you have a uniform electric field, the dipole does not see it. Okay? Now let's talk about torque on a dipole. You may not be able to exert a force on it, but you can actually rotate it. Now, viewing a dipole like this, plus Q and minus Q, that is a physical dipole. That is not a pure dipole, right? A pure dipole doesn't, it's when D is very, 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 very small. Well, how small is D? So for everything we do in coming up with formulas, we'll only hang on to expressions with D. D squared, D cubed, all of that will be ignored. Okay? So, because the parameter, let me call it, D is small, terms of order d squared and greater will be ignored. I suppose I don't need to put this in parentheses. Okay. The symbol for torque depends on the author. Remember, tau is picked for what? Volume element. So wouldn't you know it? It is N. Okay. Let's look at the dipole again. So there's d over 2 and minus d over 2. There's a plus q. There's a minus q. So it is R cross F. And I know you know this because you're also taking mechanics this semester. So I have d over 2 cross plus q times E. Listen, I want to write this. Torque on a dipole about its center. If we try to define everything, we'll be mathematicians. We cannot move forward with physics. But you know what I mean by center, right? About that point. This is E evaluated at that point. Okay? So I'm going to place my origin here. So this is my X and Y, or Z if I want it. So it is located at the point what? D over 2. Then I have, well, the other guy, minus D over 2 cross minus Q E. You know, this is what I don't want you to mistake. What this means, E is evaluated at that point, huh? It's not multiplied by, how do I make that clear? I can be notation consistent. So since I am the bearer of colored chalks, I can do this, right? Don't think of it as multiplying. So here's my notation. Or evaluated. At R. You have to find a clever way in your notes so that you don't mistake this for sums. I mean, you can mistake it for anything else. It cannot be multiplied. It doesn't make any sense. Okay? So, let me simplify. And let me also be consistent with this d squared term. This has a d already, so I don't want any d dependence. Yeah? So I can Taylor expand it and just evaluate it over here. Yeah?
We're evaluating the torque at the center.
Torque about the center, due to the two charges subject to electric field that may or may not be uniform.
So we're adding up the torques by the two charges, right? Is that
Correct. Oh, let me do, in that case, let me make this very clear, because this becomes handy. I want to simplify this to the zero, to just the order D. I don't want any more D dependence, because we have said D is so small that we're going to ignore D squared and above, or the lowest order. If D cubed is the lowest order, we're going to hang on to D cubed, right? The first non-zero term. How do I approximate vector functions like this? So a little bit of, and I can do it now or in the next section, but it's the same trouble. So if I have f of x, I can write it as f of 0 plus x times df dx, x equals 0, plus higher order terms. Correct? Let me do a 3D version of this. F of x, y, z. It is f of 0, 0, 0, plus, well, you guessed it, plus higher order terms. Correct? So let me write this vectorially to compactify notation, or f of a vector r is f of the zeroth vector plus r dot the gradient of f, except the gradient of f is evaluated at r equal to 0, plus higher order terms. Is that good? Nothing miraculous. You just have to do it, keep track of every single direction. So in that case, what is this going to be? Well, it's going to be E evaluated at 0 plus d over 2 dot gradient acting on the vector E evaluated at R. It's big notation for what's intuitive. Once you copy that down, I should tell you the difference between these two examples, except for just E and F being replaced. This is for a scalar function. This is for a vector function. So we have to keep track of all three components separately.
We have that R equals 0, evaluated R equals 0, that'd be evaluated at
D equals 0, D over 2
right,
equals.
okay, so that
It's not strict towards the end,
Huh.
right there.
after our gradient E and then
Yeah.
R equals 0.
Yeah.
So that's D over 2 equals 0.
Well, or R equals 0 at the 0 vector, if that helps. Yeah.
Does that mean it's in the origin?
At the origin of your coordinate system, where D is small. Yeah. D, from the center of the dipole. And this is true for the X component, the Y component, and Z component. But for all three components, you'll have to take D dot gradient. Yeah, this is true for any any function, so it can be the x component, y component. Good old Taylor expansion. Okay, I don't want d dependence. I don't want d dependence for my torque because there's also already a d. So which is the only term I want? If for the torque formula is the first term. So then n is equal to qd over 2 cross e at the origin, well, minus minus, at the center of the dipole. I'll be doing a problem that involves all of this, so I'm just preparing you for a collective notion. Huh.
Our minus came from that original, not.
Right, the vector is minus d over 2, the charge is minus q.
How do we get it not to be d dependent on d?
I'm sorry?
You're saying like we don't want it to be dependent.
Oh, no. We ignore the dependence of d in E because we already have a d. And d is such a small number. You know, a dipole is like an angstrom or something. Maybe not, maybe a micrometer. We don't want 10 to the 12th accuracy. That's what we mean. We're just ignoring higher order terms. There's already a d here. So this one, we only hang on to the 0th order term. What's the language? 0th order, first order, second, and we never write the second.
So-
I write the second order so infrequently that if I wanted to, I have to look up the expression.
Just to clarify, right?
Yeah.
So out of that E evaluated as D over 2, only E0, we hang on to only that.
Yep, this is
And-
this is evaluated. Let me be consistent. Sometimes it's very clear. Zero here stands for the center of the dipole.
All right, so only the E0, the term where evaluated with zero vector.
Let me avoid the confusion. Let me make this clear. Because at the end of the day, this is the formula you're using. It is literally the vector p, which is a constant vector. I want it to be same length, times the e at this point. Yeah? That's what I mean. Not times, cross. That's what I mean. Yeah? Are we good?
Yeah.
It is not a satisfactory nod.
It's the notation. I think I'm just gonna tweak it a little bit. I'm gonna use the subscript. I just
You mean to say like draw a line and put 0?
no E sub 0. That means I can read it as E evaluated at the center. I don't know.
If that floats your boat?
Yeah.
Yeah.
I think
At some point we have to do idea versus notation. Otherwise you get bogged down in notation. You take the vector P, it's a constant vector, and you do cross product the electric field. Where? At the center of the dipole. Yeah? And we're modeling dipoles literally like this. Yeah.
So without telling us the explicit torque, if we had not ignored all those terms,
Yeah.
how would that end?
Oh, there would be a d squared
I
term.
guess it'd be like a plus and then like.
Yeah, plus
more
correction
pluses and
terms.
things like that.
Yeah, yeah. D squared, d cubed, all of that. Yeah. Fine. As I'm going to do the next part, I need the older version back because I don't, let me see. Let me, what, I could write it this way or I could put, what's that?
Is torque supposed to be a scalar?
No, P cross E.
Oh, yeah, okay, yeah.
Yep, yep. Okay, now let me do force on a dipole when what? What is the case we just did before? No,
I mean, above the center?
So we just calculated the force on a dipole. I know there are too many things. We did force first, then we did torque, then we're talking about force again. The force was 0. What was the condition there?
Oh, constant electric field.
Uniform electric field. So when E is not uniform, and this is a section title. So we're doing some derivations today. It is important to see them and understand them. But more importantly, it's also, as an undergraduate, it's more important to use them in problems. And I'll spend a whole day doing one problem, because that's what it takes. Not that it's difficult, it's just long when you're calculating and being patient, that's all. This is what I want to do. Okay? So now, this is my P. I have force is equal to Q times E. You okay, James? We good? Well, I have two charges, so I write the electric field at the location of the two charges.
Why is it not negative d over 2 again?
Because it is.
Oh.
Good, good.
I thought I understood it, then all of a sudden, it's
Yeah, yeah,
the
yeah,
negative.
yeah. So, now, unlike the torque formula, there's no D outside. So we need to hang on to both the expressions. That is Q times E, oh, oops, my color coding falls apart. I know. I open and close at the same time with my green chalk. How's that?
So the more complete title would be force in the dipole when the electric field is not uniform at the center, about the center, or at the center.
Force is
Or
just
at-
net force.
Okay.
Yeah.
Also,
That's why we can take it at the center.
It's a force on an object is the net force acting on the dipole. Torque is about a point.
Yeah.
Yeah. Ashik.
just for, I don't know, what's the next term gonna be in that, expansion, just to know?
Well, I don't know what it's going to be. It's going to be d squared.
Right,
Yeah.
just d squared or?
No, I think it is di over 2 dj over 2 partial with respect to xi, partial with respect to x, j, e, and this is summation over I and j. You're welcome to carry this through.
Yeah. And, what,
I don't know that this is exactly it, but
also, why are we sticking to two terms again, only?
because d is already small.
So you only want d squared, not d cubed?
If I owe you $4.23, and back in the days when Italians had a currency, and 5 lira, would you want the 5 lira? It won't buy you anything.
Yeah.
I think like a hamburger used to cost 1,000 lira. Would you come crying for your 5 lira? No.
So,
This is already small. This is the 23 cents. This is lira currency.
so did we leave it out the first one because we already had a d, so we would have ended up with like a d squared or something? Is that what we left it out?
Yeah, we would have ended up with a d squared. Yeah, look at that, d squared. Yeah, it's just too small.
So, wasn't it too small in the case before too? Like the.
Which one?
Uniform electric field?
Right, but there was a right. In the case before we did, it's a
Right, yeah.
uniform electric field. This is 0. This was exact. Uniform.
Wait, you said the second term was 0? Or?
If it's uniform, what's the gradient
Oh,
difference?
yeah. I get you. Yeah, that makes sense.
I don't know if this is all real or made up, but it's consistently made up.
Yeah.
It works. You can't mess it up. You can't topple physics. I don't know if this is the exact expression, so I'm going to take it off.
Sometimes you gotta question the basics.
No, you have to every time. Every time. The rest is a consequence, of what you're doing. Well, guess what, guys? The E0 term cancels off, and the d over 2 plus d over 2 just becomes d, and I get q d dot evaluated where the dipole is located. And so I can finally box an expression for you. Q times D is again just P This is the force on a dipole. Obviously, when E is not uniform. Because when E is uniform, this goes to 0. And just to remind ourselves, the torque on a dipole, about the dipole, is this. Now I'm going to do one more thing. Torque on a dipole about an arbitrary point. So here my diagram looks like this. So my expression for torque is going to be, it's R cross F in general. But for us, it's going to be R plus D over 2 cross Q times E at R, plus D over 2. Plus R minus D over 2 cross minus Q E So what do I need to do? I need to,
Are we carefully making R perpendicular to the wing?
No, that was totally accidental.
It shouldn't matter, right?
Doesn't matter. It's R cross F is what it is. Whatever the math comes out to be. So I have to expand. When I expand, I have to be careful. I'm going to make you work hard for this by telling me if I'm doing this correctly. I'm going to take first this and expand with that. Okay? So Q times R cross E zero plus D over 2 dot gradient acting on E, and I'll ask you why. Plus Q times D over 2 cross E 0 minus Q. I'm just backing away, and I'll tell you when I'll have questions for you. Chip, you having fun yet? That's the expression. Martin seems happy. Seems like I have just randomly decided to keep 2 terms in certain expansion and 1 term in certain expansion. That is true. Why is that?
We have the, so in the ones where we didn't keep it, we already had a D in the parentheses.
Yep.
And the ones
Yep.
where we did keep it,
Yep.
that QR did not have a D component, so we needed.
Yep. Yep. So that means when I'm doing expansion by using these guys, I only hang on to the 0th order term. If I'm doing this has got nothing to do with anything else, so I hang on to both terms. Good. Travis, you good?
I'm not following what you just said.
So here, so obviously I have to cross multiply. There are 2 terms from this here and 2 terms from this here. So that's how I get 4 terms. When I use this cross this, this one does not have a D in it. So I hang on to the 0th order term and the 1st order D term. Because remember, we're going to hang on to up to D. But then comes this guy. This has already a D in it. So I ignore I could write it again. I could write it again over here, but this would have a D squared in it. So I just dropped it. Yeah. Okay, so then, few things should cancel. Q minus Q. These are precisely the same terms. So I get QD cross E about where? About the center of the, this is where D is 0, So, or where the dipole is located. Actually, it's at the vector R. Okay? Then comes the next term. I think the negatives will cancel. Here, the negatives will cancel. And D over 2 just becomes 1. So I have R cross QD dot all evaluated where the dipole is located. So all these terms are where E is evaluated, where the dipole is located, i.e. D is 0 or at R at this point. I can simplify this and get my final expression. This is P. Oops. Thereby finally recapping the entire lecture in that's the moral of the story. See, this is the old F. That, I mean, and this even looks nice. It's force at the center of mass times the torque about the center of the dipole. So there's nothing difficult about this except keeping track of all the terms we have derived. Now, again, the most important thing in everything that you have seen today is just understanding how to use this. If you want to compute the force on a dipole, you take the dipole vector and you dot it with the gradient operator and let it act on the electric field at the center of the dipole. That's how you get the force. Then if you want to get the torque on the dipole, first thing you do is do the torque about the center of mass. That is this R cross F. Then torque about the dipole, where P is the dipole, and the electric field is where the dipole is located. The physical dipole is considered to be just a point. D goes to 0. That's where the dipole is located. That's the conclusion for the day. All of this comes and goes too fast. So what I'm going to do on Wednesday, likely one problem. If I can do 2 problems, that'll be great. But we'll beat this horse to death by calculating. It's a fun problem. I'm doing it really for my pleasure.
Center mass of our system, like hypothetically, we have some kind of mass here, maybe our dipole has some kind of mass.
I mean, for the dipole, it's right here.
Okay.
Yeah.
Okay.
Are we good? That is by definition. That's how I've drawn it. It is not the true center of mass. If it is a water molecule, if it is, hydrogen is much smaller than the oxygen, well, the dipole is somewhere over here. Whatever is the center of mass is what I'm indicating to be this point in my cartoon. And understanding physics through these simple cartoons are also very important. The way to understand things, you might wonder if it's an old Jedi mind trick, is by a cartoon drawing and clever naming of things that tells you that certain properties are true. So that, for example, if it's a conserved quantity, conservative force, the energy is conserved. If you do physics all the time, you know that's a simple derivation, but otherwise, the word is suggesting it. Conserved quantity, conservative force, energy is conserved. You don't have to know much about the discipline. Just by one of the greatest names, scientific naming of things, is a black hole. You don't have to know general relativity, but you know what goes in is not coming out unless you study, of course, Hawking radiation. Yeah, so yeah, things get out of Las Vegas. So what happens in Las Vegas doesn't stay in.